Let me now say a few words about polynomials with coefficients in rational, real, and complex numbers. So the field Q is the field of rational numbers, R is the field of real numbers, and C is the field of complex numbers. These notations are very standard throughout mathematics. These semi-bold letters are used widely. Let me start with the ring of polynomials with coefficients in Q. So for our field F, we consider Q the field of real numbers. I will only briefly discuss results from the corresponding section in the book, and I will give no proofs. That is because this is section 4.5. That is because the proofs there are no conceptions beyond high school algebra. At the same time, these proofs are not easy. So these are lengthy and sometimes a bit tricky manipulations, although conceptually there is nothing but high school algebra involved. Theorem 4.21 in the book allows one to find all rational roots of a polynomial with rational coefficients. However, if a polynomial has no roots, it may be still reducible. So this theorem does not allow, in general, does not allow for finding whether a polynomial is irreducible or reducible. But may not allow one to find out whether a polynomial is irreducible. Here is an example. I write here a polynomial with rational coefficients x squared minus 2x plus 5 times x squared minus 2x plus 7. If you multiply it out, this is a polynomial with even integral, not just rational coefficients. This polynomial is not irreducible. It is reducible because it is written as a product of two polynomials. At the same time, neither of these polynomials, that's easy to check, that's quadratic with negative discriminants, and they don't have even real roots, therefore they don't have rational roots. However, when you multiply it out, it may become quite difficult to find this sort of factorization for a polynomial of degree 4, which you obtain this way. The polynomial is going to be of degree 4 after multiplication. It is reducible. We know that in advance. It does not have rational roots, and if you don't know the factorization in advance, it is not an easy task to find it. Thus, a question about whether a polynomial in this ring is irreducible or not becomes quite difficult question. So the following theorem provides with a criterion of irreducibility. The theorem is formulated for polynomials in Z of x with integral coefficients. You may always clear denominators for a polynomial in Q of x multiplying by a unit, an element of Q, and make it a polynomial with integral coefficients. That does not influence irreducibility. Both the polynomial with rational and polynomial with integral coefficients are reducible or irreducible together. That's the content of theorem, quite technical theorem 423. Tells us that a polynomial polynomials from Q of x and Z are irreducible together. So you take a polynomial, multiply it by an integer so that all coefficients become integral. That does not influence the irreducibility of a polynomial. That's what theorem 423 tells you. After that, you have the criterion, Eisenstein criterion, given in theorem 421. Let a n x n plus a1 plus a1x plus a0 be a polynomial with integral coefficients. Z is not a field, that this is a ring. Does not matter. We address irreducibility of this polynomial as a polynomial in Q of x, say. Let P be a prime if the following conditions are satisfied. P divides the coefficients, all of them, but the leading coefficient. So for P divides AI for I from 0 up to n minus 1. P does not divide an, and P squared does not divide a0. Does not divide a0. If these conditions are satisfied, then the polynomial, or call this polynomial f. We typically wrote it from a0 till an. I wrote it in the inverse order. That is the same polynomial, of course. Or let me I will keep it this way. Typically, they keep it this way in the examples. So if these conditions are satisfied, we can find the prime which divides all coefficients except the leading one, does not divide the leading one, and P squared does not divide a0. Then f, the polynomial, is irreducible. In Q of x. As I said, the proof is a little bit lengthy and tricky, although does not use any concepts beyond high school algebra. Such a polynomial is called Eisenstein polynomial. So it's Eisenstein criterion, and we call such a polynomial terminology Eisenstein polynomial. For the prime P, you typically gotta specify what is the prime. I immediately have to say that although this is a very useful and powerful criterion, not every irreducible polynomial is Eisenstein. So that's remark. Don't get misled by this theorem. The converse is definitely false. Not every irreducible polynomial is an Eisenstein let me give a couple of applications, examples, how one can apply this criterion. First, one can easily write down, so first application, there are many. I want just to illustrate the criterion with some applications. One can easily write down an irreducible polynomial of any degree and bigger or equal than 1. Here we go. Example. X to the n minus 2 for any n bigger or equal than 1 is an Eisenstein polynomial at p equals 2. For p equals 2. Therefore, irreducible. Indeed, the leading coefficient is 1, not divisible by 2. All other coefficients are zeros, and the constant term is 2. 0 is divisible by everything, by 2 in particular. The constant term 2 is divisible by 2, so this is n. So, n minus 1, it was correct. It was correct, sorry. No. Yes, all correct. So, leading coefficient is 1, not divisible by 2. Constant term is divisible by 2. A naught is divisible by 2, but among others. But is not divisible by 2 squared. 2 is not divisible by 4. This polynomial is irreducible. By the way, we conclude that this polynomial has no rational roots. It follows that nth root of 2 is not a rational number. There is no rational number such that its nth power for all n bigger than 1, n equals 1, the polynomial is still irreducible, but it has a root. Otherwise, for n bigger than 1, it is irreducible, thus has no roots. Thus, there is no rational number whose nth power is 2. That is a one-line proof of a vast generalization of the fact that root of 2 is not a rational number. Oh. Better, I wrote that for brevity, better to say there is no rational number whose nth power is 2. This polynomial is irreducible, therefore has no roots. Another example of how the criterion may be applied, there is exercise 12 in this section. It is an easy and immediate exercise. I will not do it now, which tells you that let f be a polynomial over any field with coefficients in any field, and let C be an element of the field. So let say G is f of x plus c. We plug in for x plus c, and produce another polynomial. G is also a polynomial with coefficients in x. The exercise tells us that f and g are reducible or irreducible together. Or, say, put it so, f is irreducible if and only if g is irreducible. That is a very, very simple exercise. You write factorization. If f is not irreducible, then you prove g is also not irreducible. You write the factorization for g, produce out of that factorization for f, or backwards. So that is a very easy exercise, how to produce factorization of one polynomial out of another one. You simply plug in x plus c or x minus c, depending on whether you start from g or from f for x. And one factorization becomes another one, so you prove that the two polynomials are reducible always together. One non-trivial factorization immediately implies another non-trivial factorization. Now, exercise 13 is based upon that, and that is about an application of Eisenstein criterion. they ask us to prove that the polynomial x to the 4 plus 4x plus 1 as a polynomial with coefficients in Q is irreducible. If we go back, I gave an example of reducible polynomial of degree 4, where it is probably difficult to find the factorization after you multiply out. Here is another polynomial of degree 4 where you do not have a factorization into two polynomials of degree 2. What you can do here, of course, it is possible, because 4 is not that big, it is possible to do it in a straightforward way. I just want to show you how to do that with Eisenstein criterion. You use the previous exercise. Yeah, by the way, we are going to prove that this polynomial is irreducible. The polynomial itself, in the first place, is not an Eisenstein polynomial. There is no such a prime which divides 4 and 1. More precisely, so for Eisenstein criterion, there should be a prime which divides all coefficients of the polynomial except the leading coefficient. In this case, constant term is 1, so it's not divisible by any prime. However, you take this c to be 1 and write the polynomial x plus 1 to the 4 plus 4 times x plus 1 plus 1. You multiply everything out to find that this is x to the 4 plus 4x cubed plus 6x squared plus 8x plus 6. So now it turns out that this polynomial is Eisenstein This is an Eisenstein polynomial for the prime 2. Indeed, the leading coefficient is 1. All other coefficients are divisible by 2. 4 is divisible by 2, 6, 8, 6. All divisible by 2, and that, again, let me show you. So all coefficients divisible by the prime, except the leading term, and the constant term is not divisible by square of the prime. So indeed, all coefficients except constant term, instead the leading coefficient, are divisible by 2, and the constant term 6 is not divisible by square of 2, which is 4. This is Eisenstein polynomial for p equals 4, therefore irreducible. Now we can go back and use the statement of exercise 12 with c equals 1. This becomes the g from this exercise with c equals 1, and this polynomial is irreducible. That implies that our original polynomial was also irreducible. Implies x to the 4 plus 4x plus 1 is irreducible by exercise 12 with c equals 1. Let me know. That is all I wanted to tell you about polynomials with rational coefficients.